Hello everyone, my name is Pranav Teja. Welcome to my quick concept video presentation of the subject applied physics. And first of all, let me introduce myself. I am Pranav Teja. Roll number is 2195186688. This is my concept video. Subject applied physics. I am from branch CSC AIM. The topic for my concept video is evidence of diffraction and interference. Now, these two topics are most important when it comes into diffraction of particles. These two topics are very important when we uh, discuss particles and their behavior, how they behave, and what are the properties of the particle. Will be able to know its behavior by these two uh, topics two by these two phenomenon that takes place. These two phenomena are groundbreaking revolutions. I i think this evidence of the diffraction and interference is the one of the most important topics in physics. Let us get started. Let us move forward. First of all, what is diffraction? Light is a transverse electromagnetic wave. Diffraction and interference are phenomena observed with all waves. Diffraction is a tendency of a wave emitted from a finite source or passing through a finite aperture to spread out as it propagates. Diffraction results from the interference of an infinite number of waves emitted by a continuous distribution of source points. According to Huygens principle, every point on a wavefront of light can be considered to be a secondary source of spherical wavelets. These wavelets propagate outward with the characteristic speed of the wave. The wavelets emitted by all the points on the wavefront interfere with each other to produce the traveling wave. Huygens' principle also holds for electromagnetic waves. When studying the propagation of light, we can replace any wavefront by a collection of sources distributed uniformly over the wavefront radiating in phase. When light passes through a small opening comparable in size to the wavelength lambda of the light in an otherwise opaque obstacle, the wavefront on the other side of the opening resembles the wavefront shown on the right. This is the obstacle. When light is passed through this, there we can see the wave fronts which are formed like this. This is a single slit diffraction. This is the evidence of the diffraction that we are seeing. Basically, what happens is when light passes through an obstacle where a small amount of length is uh, open in that obstacle, That is where the diffraction point occurs, and this is a very important point to be noted. But let's move further. The light spreads around the edges of the obstacle. This is the phenomenon of diffraction. Diffraction is a wave phenomenon and is also observed with water waves in a ripple path. A single large slit. When a large amount of space is open to that obstacle, ripples are formed in this way, not in a circular way, but in a small gap. The wavelengths are formed approximately circular and perfect wave fronts are formed. See, this phenomenon is called diffraction. Diffraction is a wave phenomenon and is also observed with wavefronts in a ripple tank. The single slit. When light passes through a single slit whose width W is on the order of the wavelength of the light, then we can observe a single slit diffraction pattern on a screen that is a distance L greater than W away from the slit. The intensity is a function of angle. Huygens principle tells us that each part of the slit can be thought of as an emitter of waves. All these waves interfere to produce the diffraction pattern. When crest meets crest, we have constructive interference, and where crest meets trough, we have destructive interference. Very far from the point source, the wave fronts are essentially plane waves. This is called a Fraunhofer regime, and the diffraction pattern is called Fraunhofer diffraction. The position of all maxima and minima in the Fraunhofer diffraction pattern from a single slit can be found from the following single arguments. Consider a single slit of width W as shown in the diagram on the right. A plane wave is incident from the bottom and all points oscillate in phase inside the slit. For light leaving the slit in a particular direction defined by the angle theta, we may have destructive interference between the rays at the right edge and the middle ray 1 and the middle ray 7 to arrive at a distant screen perpendicular to the direction of propagation of the rays. The rays coming from different points inside the slit have to travel different distances. They have a different optical path length. If ray 7 has to travel an extra distance if one half wavelength, that's lambda by 2 compared to ray 1, then ray 1 and ray 7 destructively interfere. Crest, so crest meets trough. This is the figure representing single slit diffraction that shows the evidence of the diffraction of a particle. In the first figure, we are seeing this when the small particles or light particles are traveling. When it when it hits this obstacle, passing from the small opening, the diffraction is occurred like this, and on the screen, the maximum fringe or intensity of the fringes is maximum at the middle, and as it moves far away from the maximum, then the the intensity of the fringes reduces. In the below figure, we can see clearly. First, let us go step by step. What is happening? What is the process? Is so here is a monochromatic light source, laser light. Laser light is being projected on the obstacle. This is an obstacle. Light waves emitted by the source. Screen with a narrow single slit. This is called a narrow single slit. This is a screen. So this monochromatic light source, that is laser, is traveled in this direction, and this through this single slit the waves are formed like this. Light waves are diffracted like by the slit. So on the screen it is formed. So the fringe pattern is occurred in this manner. At the center, the maximum, where the center maxima is located, the intensity of the fringes is maximum, and these are the first, second, and third maxima respectively. As we go to the left part and the right part. I hope I made it clear. If the optical path length of two rays differ by lambda by 2, the two rays interfere destructively. For ray 1 and ray 7 to be half a wavelength out of phase, we need W by 2 sin theta is equals to lambda by 2, or W sin theta is equals to lambda. But for geometry, if these two rays interfere destructively, so do rays 2 and 8, 3 and 8, 6 and 8, 8 and 5 and 11, 6 and 12. In effect, light from one half of the opening interferes destructively and cancels out light from the other half. Destructive interference produces the dark fringes. Dark fringes in the diffraction pattern of a single slit are found at angles theta, for which W sin theta is equal to m lambda, where m is an integer. M is equal to 1, 2, 3, and so on. For the first dark fringe, we have W sin theta is equal to lambda. This is the actual original pattern of the fringes that is observed on a, on the screen. This bright fringe at the middle is the central maxima. This is a formula. W sin theta is equals to lambda. The two rays interfere destructively. For the first dark fringe, we have W sin theta is equals to lambda. To find where the first dark where the spots where the dark fringes are present, we use this formula. W sin theta is equals to lambda. When W is smaller than lambda, the equation W sin theta is equals to lambda has no solution and no dark fringes are produced. If the interference pattern is viewed on a screen at distance L from the slits, then the wavelength can be found from the spacing of the fringes. We have lambda is equals to W sin theta by M, and sin theta is equals to Z by L square plus Z square to the power 1 half, or lambda is equals to ZW by M into L square plus Z square to the power half, where the Z is the distance from the center of the interference pattern to the mth dark line in the pattern. If L is much more greater than Z, then L square plus Z square to power half is approximately equals to L, and we can write lambda is equals to ZW by ML. This is the pictures. I hope you have understood it clearly. Now we'll come to now we have discussed in diffraction through the evidence of diffraction by the single slit experiment. Now we are going to see the double slit experiment, which shows the proof of the interference nature of the particle. So double slit. If light is incident onto an obstacle which contains two very small slits a distance d apart, then the wavelets emanating from each slit will interfere behind the obstacle. Waves passing through each slit are directed and spread out at angles where the single slit diffraction pattern produces non-zero intensity. The waves from the two slits can now constructively or destructively interfere. If we let the light fall onto a screen behind the obstacle, we will observe a pattern of bright and dark stripes on the screen. In the region where with a single slit we only observe a diffraction maximum. This pattern of bright and dark lines is known as an interference fringe pattern. The bright lines indicate constructive interference and the dark lines indicate destructive interference. The bright fringe in the middle of the diagram on the right is caused by constructive interference of the light from the two slits traveling the same distance to the screen. It is known as the zero-order fringe. Crest meets crest and trough means trough. The dark fringes on either side of the zero-order fringe are caused by destructive interference. Light from one slit travels a distance that is half wavelength longer than the distance traveled by light from the other slit. Crests meet troughs at these locations. The dark fringes are followed by the first-order fringes, one on each side of the zero-order fringe. Light from one slit travels a distance that is one wavelength longer than the distance traveled by light from the other slit to reach these positions. Crest again meets crest. So in this figure we'll know what it means. This is electron beam gun. The electrons are struck on this double slit screen and the interference patterns is observed like this. The pattern is observed like this on the screen. So double slit experiment. As in the single slit, there was only one slit, one narrow slit on this obstacle on the screen. But in this double slit experiment, we are going to have two slits like this, and the wavefronts that are observed they interfere and form the bigger wavefront, and the interference pattern is observed on the screen as in this pattern. Like this it is formed. These light rods, these are rays of light coming from the source reach the slits. Interference of light waves due to two tiny slits and narrow arrow indicate direction of wave propagation. Alternating bright and dark fringes due to interference of light waves. The diagram on the right shows the geometry for the fringe pattern. If the light with wavelength lambda passes through two slits separated by distance d, we will observe constructively interference at certain angles. These angles are found by applying the condition for constructive interference, which is d sin theta is equals to m lambda, m is equals to 0, 1, 2, and so on. The distances from the two slits to the screen differ by an integer number of wavelengths. Crest meets crest. The angle at which dark fringes occur may be found by applying the condition for destructive interference. The distance from the two slits to the screen differ by a integer number of wavelengths plus half wavelength. Crest meet trough. In this situation, if the interference pattern is viewed on screen a distance L from the slits, then the wavelength can be found from the spacing of the fringes. We have sin theta is equal to Z by L square plus Z square to the power 1 half, and lambda is equal to Z d by m into L square plus Z square to the power half, where Z is the distance from the center of the interference pattern to the mth bright fringe in the pattern. If L is much greater than Z, then L square plus Z square half is equals to the power half is approximately equals to L, and we can write lambda is equal to Zd by m into L. So this is the figure of the diffraction of light when it comes in double slit experiments. This is the diffraction, interference pattern that is observed, which is to be noted important. This is the laser light passing through a single slit showing basic diffraction pattern. This is the double slit pattern. Note the interference fringes on the top of the diffraction pattern. Thank you for spending your time on my concept video. I hope I made it clear the evidence of the diffraction and interference of the particle through single slit and double slit experiments. Thank you all.